Hi everyone. So today we're going to look at this example here. So we've got a point charge that's 6 nanocoulombs and it's at rest at the origin of a coordinate system. Alright, so if we're drawing something, here's our coordinate system. Alright, and here at the origin, we've got some charge, maybe let's call it Q1, and we're told that's 6 nanocoulomb. I'll write about sig figs at the end. Looks like we've got 3 sig figs in this problem, because 6 is 3 sig figs. Anyway, so we have an external force exerted on a 12 nanocoulomb point charge to move it from point A, that's at 230 centimeters, to point B, that's at 150 centimeters, while the point charge at the origin remains at rest. Alright, so let's sketch that out. So we have charge 2 starting over here, so that's 12 nanocoulombs. And it starts at location A, which is 230 centimeters. Let's convert to meters, so 2.3 meters. And then it's going to travel to point B. I'll put that over here because that's at location 1.5 meters. So I'm going to draw like an arrow here just to remind myself that our charge 2 is traveling from A to B. Alright, so we're told to apply energy principles to calculate the work done on the system of point charges if the 12 nanocoulomb charge begins and ends at rest. So, since we're dealing with energy principles, right, basically meaning we start with the work energy system theorem, which means we have to define our system. So, let's see. For our system here, let's include both charges. So if we do that, then the forces that are internal to our system are going to be the electric force, and external is going to be this external force that they state in the problem. Right? So we'll just call that F external. Right? You might think maybe we have to worry about gravity, right? Because there's going to be some gravitational attraction between these charges. And that could be very true. You can call that an internal force, but then you might think, well, do these charges exist on the Earth? So do we need to worry about the gravitational force to the Earth, which would be external? Now, thinking about this, right, we're dealing with the electric force, and we're dealing with a short range distance here. So the electric force is going to be much, much larger than the gravitational force at this range. Right? So in dealing with this then, our gravitational force is going to be negligible, so we're just not going to worry about it. So our internal force is the electric force, and external is going to be our external force. You can call it an applied force if you want. So in looking at this, right, this allows us to apply our work energy theorem. So I'm going to scroll here. So our work done by our external forces, that's just our external force, is equal to the change in energy of our system. Right, so thinking about the types of energy that we have, since the electric force is internal, we're going to have electric potential energy because of that. So we have to worry about the change in electric potential energy. And then every single time we're going to have to worry about kinetic energy, right? So we have to worry about the change in kinetic energy. And then we don't have any other types of energy in our system. So looking here, let me actually scroll up a little bit. We see here that the problem tells us that this charge that's moving begins and ends at rest. That's very useful. That means our kinetic energy starts at 0, ends at 0, making it overall 0. All right. So before I start, computing things, right, we see here that the work done by our external force is going to be the change in electric potential energy. Now I'm going to think about whether I expect this to be a positive value or a negative value before I move on. Right? So here we're dealing with 2 positive charges. So if we kind of think back to what the electric potential energy graph looks like for 2 positive charges, right? So they're repulsive. So it's electric potential energy versus position, the relative position of 2 charges, is going to be the positive quadrant of hyperbola. So based on that, and we'll kind of apply a little bit of reasoning, right? But as the distance between the charges gets smaller, that potential gets bigger, right? And we can can see that here, right? So as our charge, we have to apply some sort of force to force these charges to get closer together, right? Because naturally they want to move apart. They repel each other because they're both positive charges. So in bringing them closer together, thinking about its electric potential energy, it depends on distance, bringing them closer together is going to increase that potential value. The potential energy value. So if our energy of this system is going to be increasing when we bring it together, that means we're going to be doing positive work on our system. Because remember, positive work adds energy, or positive work done on our system adds energy to our system. So we expect that the work done by our external force is going to be positive. All right, so let's hope that happens. Okay, so we can get a little more computational now, right? Because we know we have a formula for the electric potential energy at a location, right? That's going to be K, Q1, Q2 over R. Right? So if we're dealing with the change in K, right, that's going to be K, Q1, Q2 over, let's see, so change in is final minus initial, so this is final distance between the charges, minus K, Q1, Q2 over R initial. So I could simplify this, so I can plug in less numbers and factor out K, Q1, and Q2, because those are constant values. So we're left with that over 1 over Rf minus 1 over Ri. So just something to be careful with, something that's easy to, I'm a little bit sloppy here. I should have this be delta U is equal to, sorry about that. Anyway, something to be careful with is math, right? So you might think, all right, so we're dealing with change in electric potential energy, so that's just K, Q1, Q2 over, well, change in R is changing, so it's delta R. That's wrong, all right? Comparing that to the math we just did, we see that they're not equivalent, right? Putting just delta R in the denominator is not the same thing as doing this. That's not how fractions work. It's not how math works, right? And in fact, that's going to be so wrong as to if we did this, we'd actually end up with a negative potential value because we're dealing with delta R, so that's final R minus initial R, so 1.5 minus 2.3, that's a negative value. And we expected that our work to be positive, not negative, right? So that can be kind of a sign that something went wrong. So if we plug in numbers to our expression we have up here for our change in electric potential energy, which is our work, let's see, let's plug in numbers. So we've got K, so that's 9 times 10 to the 9 Newton times meter squared over Coulomb squared. Q1 times Q2, all right, so 6 nanocoulombs and 12 nanocoulombs. So that's 6 times 10 to the negative 9 coulombs times 12 times 10 to the negative 9 coulombs. All right, and let me scroll a little bit this way so I can make it fit all on one line. And we need to multiply it by 1 over Rf. Well, so our final location is the 1.5 meters minus 1 over Ri. So our initial distance between the two charges is 2.3 meters. All right, so if we plug this all in, actually, no, let me just zoom out a little bit, that way you can see the work. We find that the work done by our external force is equal to 1.5. Oh man, I rounded the wrong number of sig figs. I only rounded to 2 sig figs, but we should round to 3. No, deal with it. All right, 1.5 times 10 to the negative 7 joules. All right, so that value is positive like we expect. It's a pretty small amount of energy. And that's to be expected because we're dealing with small amounts of charge here. Nanocoulombs is a small amount of charge. Typical amount of charge you're dealing with electrostatic problems. But nonetheless, that's what we've got. All right, so let's look at part B. Part B states that the same point charge is released from rest at point B. Okay, so now it starts at point B, while the charge at the origin, again, remains at a fixed position. What is the kinetic energy when it passes through point A, and how could we find the speed of the particle? All right, so we're dealing with kinetic energy, so it looks like, again, we're going to be dealing with energy quantities. But now we don't have any external force in our system. So in thinking about this part here, part B, now if there's no external forces, then we don't have any change in energy. Energy is conserved. So our change in energy is going to be equal to 0. So because now our only forces the only force that we're dealing here is actually the electric force, and let's include that in our let's include both charges in our system, so that way that force is internal. So therefore, our change in energy is going to just be the change in electric potential energy plus the change in kinetic energy. And this time, the change in kinetic energy is not 0, right? Because it goes from 0 initially to moving in the end. So actually, when we deal with final minus initial kinetic energy, the initial kinetic energy is 0. So we're just dealing with the final kinetic there. So we have here that 0 is equal to change in electric potential energy plus our final kinetic energy. So our Kf is negative delta UE, where, hey, wait a second, in the part before we solved for delta UE, right, and said that was equal to the work. And you might think, uh-oh, you might have a problem, right? Because looking at this here, we've got 1.5 times 10 to the negative 7 joules. We plug it in here, we end up with the kinetic energy having a negative that number. And kinetic energy can never be negative, right? It's 1/2 mv squared. It's always a positive value. Now, not a big problem actually, because the one thing we have to be careful with is in this problem, we're moving from point B to point A, whereas previously we moved from A to B. So really, when we're plugging in the amount of work done, our work is actually a negative this quantity because we flipped our initial and final positions. So basically, if we were to compute things from scratch, right, we're using this expression here, right, but now these two quantities switch locations. So then, plugging things in, we have negative times negative 1.5 times 10 to the negative 7 joules, giving us just 1.5 times 10 to the negative 7 joules. So that's its kinetic energy at that location. So pretty straightforward, pretty simple. And the next question asks, how could we find the speed from this? That's pretty simple and hopefully straightforward. You just set that equal to 1/2 mv squared. Right? So in order to actually solve for the speed, we would need to know the mass of charge number 2 in our problem. All right, so I hope that was helpful.